Hi everyone, welcome to Seismic Data Processing course. So we finished the pre-processing and the main processing. Today we have the migration. We have two types of migration. The one is applied pre-stack migration, and this is time pre-stack time migration, a pre-stack depth migration, and we have post-stack migration. So what is the migration? Seismic migration is the process of reconstructing a seismic image. So the reflections event, reflected seismic wave are repositioned at their correct locations beneath the surface. So essentially it's correct for distortion in the raw seismic data caused by the geometry of the subsurface and the angles of the reflectors. Why would you need the migration? The initial or stacked seismic sections is not a true representation of the underground geometry. Migration adjusts this to create a more accurate image of the subsurface layers. Was the main purpose of the migration to move dipping reflections to their true positions and also to collapse diffractions patterns and improve resolution. So why the migration? On the seismic trace we have the common midpoint, and that is the source and receiver, and on the seismic trace they assume the common depth point is directly below the common midpoint. The common depth point is directly below the common midpoint in case of you have horizontal layer, but most of the case we have dipping layers. So when you chord the reflections, it will assume that the common midpoint is directly below the common depth point, and it will not give you the real reflections. The real reflections should be like this with the angles. It will assume this common midpoint is coming vertically directly beneath the common depth point. It will view this way. So that's why we need to do the migration to back these reflections, to shift this reflection to their true geological subsurface layer. We have the type of migration. We have four combinations possible: pre-stack time migration and pre-stack depth migration. This happened before stacking, and post-stack time and depth migration. This is happened after the stacking. So this then increase structural complexity. This is the complex method. Pre-stack to be complex, pre-stack complex, and there's no complexity. Post-stack time migration and post-stack depth migration will be not complex, and pre-stack time migration and depth migration will apply before the stacking. It will be low, but it will take a lot of time, but will be more accurate than the post-stack. So this is the explanation case. We have the dipping reflections. This is the normal case. This is the actual reflector. We have this the surface. These are the receiver. So when you have the reflectors is coming from this direction, it will assume on the receiver these reflectors come from vertical beneath line beneath the receiver, and this is the true vertical. This is the true reflections, but it will assume these reflections will come on the seismic trace. It will assume these reflections coming from direct vertical line beneath the receiver. Direct vertical line beneath the receiver, but it's actually coming from different angles. So this is the recorded data. This is the blue line. It will be the recorded reflections on the seismic trace, but we need to calculate the actual reflections. So that's why we do the migration. We have to calculate this is the angle in here, to calculate the real angle, and then we have the tan for the real stacking angle. And in the case of we have the red intake line, and we have this the real reflections, and will give you this assume this reflections, and this the real reflections, and the blue one will assume is coming from direct vertical line beneath the receiver. And so you will have on the seismic trace very big intake line, but in case we have very small intake line, and that's why we need to do the migration to back to the true geological subsurface layer. In the case of scenic line, so these are the real reflections, but this is beneath the geophone. You will have these reflections, the false reflections, and then you will have something called bow tie. This is the bow tie, and this is the bow tie is just because we don't do the migration. So this is the scenic line in here. This is the earth model, and this is the unmigrated seismic data. You will have the bow tie in here because the scenic line. After migration, you will have only the scenic line very clear in here. And also this is a real example. This is the bow tie in here in case of scenic line, and this is to have the scenic line, the real scenic line after migrated. We have different type of domains of migration. One, this is the theories for wave theories or ray theory, and we have in case of subsurface geology we have isotopic or anisotopic, and in case of we have wave properties we have acoustic, elastic, and inelastic, and in the case of dimensions we have 2D and 3D and 4D dimension. So advanced classification of seismic migration, we have the seismic migration, this is wave field extrapolation, and we have integral solution. Within the wave field extrapolation we have one-way wave equipment and two-way wave equipment. And one-way, this is the Fourier, phase shift plus interpolations, and within two-way wave equation we have reverse time migration and full wave from inversion. This is the difference between integral method and this is wave field extrapolation or continuous method. This is the strength, and we have the strength and the weakness and the weakness. This is deliver subset of the image volume. This is the images all arrival, and this is good dip response, and this is more accurate amplitude treatment. This is the complexity conversion. So we're starting from the pre-stack time migration, and then we go to pre-stack depth migration. The complexity will be more, and then we have pre-stack. This is full beam pre-stack depth migration. It will be more complexity, and also we have the reverse time migration. This is the more complex. And two domain where image technique are applied. We have two domain when the migration is applied, the 2D or 3 domain, and we have the common offset domain. Within the reverse time migration method we have gas dag migration and phase shift migration and stalled constant velocity migration. So this is we lost the dip component of image. This is the equation too. And also we have the phase shift migration. This is the constant velocity concept was removed, which was imposed by stalled. This is the equation. And also we have this 1978 stalled based on the 2D FK migration. This migration data exactly up to 19 degree, and this high speed and low computational power. And this is the equation. So this is all you need to know about this migration, and we'll continue the next lectures. So thank you for watching, and see you in the next video.